and particularly the HR diagram. We have already discussed the equations that govern a star which is burning hydrogen, and these equations yield solutions for the mass range 0.06 to 120 solar mass. So, what happens for masses which are smaller or larger than this? Suppose I take a star whose mass is less than 0.06 solar masses and apply the equations of hydrostatic equilibrium, the mass distribution, luminosity distribution, etc., and solve them. It turns out that the density and temperature at the core are not adequate for hydrogen burning. So, if you have a mass smaller than this, the nuclear fusion process does not start off. That is the basic thing. So, you do not have a star. If you have a mass which is greater than 120 times the solar mass, then what happens is that the luminosity exceeds the Eddington luminosity. And let me remind you, we have discussed the Eddington luminosity in a problem earlier, and if the luminosity exceeds the Eddington luminosity, the radiation pressure is adequate to blow out the outer layer of the star. The gravitational attraction is not sufficient to hold it, balance the radiation pressure. So, if you solve those equations for a star of mass greater than this, the luminosity is so high that the outer layer of the star gets blown apart due to the radiation pressure, and you do not have a stable solution. Okay. So, you find solutions in this mass range. Now, corresponding to this mass range, the radius of the star varies between 0.1 to 150 to 15, sorry, 15 times the solar radius. Okay. So, the point to note here is that the mass range, the ratio of the largest mass for which you can have a hydrogen burning star to the smallest mass is a factor of 2000. Whereas, for this mass range the radius does not change, it is not very sensitive to the mass. The radius changes only by a factor of 150. Okay. Does not increase proportionately, it is a very somewhat weak dependence. But if you look at the luminosity, so you solve that equation and determine the luminosity of the star, solve the set of equations, and 4 equations which we had discussed and look at the luminosity of the star. The luminosities range between 0.011 to 8 into 10 to the power 5 solar luminosity. So, the luminosity is extremely sensitive to the mass. And you change the mass by a small amount, the luminosity goes up enormously. Okay. This is a factor of 10 to the power 8 variation in the luminosity. So, the brightest star is 10 to the power 8 times brighter than the faintest star which you can have, provided the stars are burning hydrogen. Okay. So, these are all what we have been discussing till now are all solutions of the 4 equations which we had written down, and they cover this mass range. You have solutions for the mass range which I told you for this mass range, and the corresponding range of radii is this, and the range in the luminosity is given over here. Okay. Now, the temperatures. Okay. So, the temperature, okay, the stars can be classified. Let us now have a look at the classification of this of the stars. So, for the different masses you get stars of different temperature, surface temperature, and the stars can be classified based on their temperature, which is also indicated by the spectrum. So, this is called spectral classification. So, the spectrum is a direct indication of the temperature, and the hottest star is classified as O. The O stars are the hottest, and the M star are the coolest. And observationally, this manifests itself in the spectrum of the stars. So, in the O stars you get helium absorption spectra, you get helium absorption lines, to excite helium you have to produce ultraviolet radiation. So, these stars, O stars, produce copious amounts of ultraviolet radiation which is adequate to ionize helium. So, you can observe helium absorption lines, whereas in the M stars you get metal absorption lines. These are the two extremities. The whole spectral classification is as follows. So, the hydrogen burning stars. Okay, before I proceed any further, a point which I should have mentioned earlier: stars which burn hydrogen these are referred to as main sequence stars. And why it is called the main sequence I shall explain to you shortly. Okay, so, we shall interchangeably be terming them as hydrogen burning stars or main sequence stars, and the equations which we had developed are for these classes of this class of stars. Now, in general, stars can be classified into based on their spectrum, and the spectral classification scheme is as follows. O stars are the brightest, hottest stars, M stars are the coolest stars, and you have different spectral classes in between. So, let me write down the entire spectral classification scheme it is as follows: O, and there is a mnemonic by which you remember it. So, let me tell you the mnemonic also: O B. So, focus only on the capital letters: O B A, fine, girl or guy, whichever you prefer, kiss me. So, this is the mnemonic by which astronomers remember the entire spectral classification scheme, and the different spectral types are O, B, A, F, G, or it could be this, K, M. The O stars are the hottest and the M stars are the coolest. Okay, and this is a mnemonic by which you can remember the spectral classification scheme. There is a further subdivision inside this. So, the B stars, for example, so you can have a classification, a sub classification. So, the sub classification is say B0 to B9. Okay. So, this holds for all of them. So, 0 to 9 is the subclass. For each spectral type, again you have a subtype, subclass, which is labeled by the number 0 to 9, where this is hotter than this. Okay. So, the temperature is essentially inferred from the spectrum straight away. Okay. Now, given the same temperature, it turns out that you can have classes of different luminosities also. So, to indicate this, there is another index which indicates the luminosity, and this runs from 1 to 5, and 1 are the giants. So, the 1 are the most luminous stars, 5 are the least luminous, are the lesser luminous stars. So, 5 refers to the main sequence. Stars. 1 refers to giants, which we shall come to. Okay, supergiants, giants. So, this is a luminosity classification. In addition to the spectral classification, you also have a luminosity classification which tells you the luminosity. So, the sun, for example, the sun is classified as G 2 5. Okay, that is the classification of the sun. To just have a look, where does the sun lie? The sun is a typical star, very ordinary kind of star, and it is not a very hot star, neither is it a very cold star. It lies somewhere in the middle of the spectral classification scheme. It is a G star. There is a sub classification 2, which is somewhat towards the hotter side amongst the G stars, and it is a main sequence star burning hydrogen, which is indicated by 5. So, you could have a G star which is not on the main sequence also. Okay, so, the G2 is an indication of the temperature, this is an indication of the luminosity. This is how stars are classified observationally, and this is an outcome also of the equations. So, the equations also, if you take a mass and solve the equations, you will get from the surface properties, you will get the spectral classification class, and you will get the luminosity also. Okay. Another outcome, a very interesting outcome, is the convection, whether the energy transport is convective or radiative. Again, we have discussed this, and I have told you that the criteria for deciding which of these will occur is that if the temperature gradient, so if we have radiative transport, and if the radiative temperature gradient, if this exceeds the adiabatic transport temperature gradient, then we have convection, and convection is a very efficient means of transporting energy. So, the temperature gradient then does not exceed this value, it remains at this value. So, with a lower temperature gradient you are able to transport more energy. Okay. Now, so the equations, when you solve these equations, the 4 equations with the extra conditions that we have discussed, it turns out that for low masses the energy transport is entirely convective. And then as you keep on increasing the mass, once you cross 0.4 times the solar mass, so once you cross this, you develop a radiative core. The convection region gets smaller and smaller, it is outside. So, the envelope is convective. So, the core is radiative, the energy is transported radiatively in the core, and the envelope, it looks like this. So, you have radiative transport here, and then you have convection in the outer parts. I have just drawn a little part of it. Then as you keep on increasing the mass, if you look at stars of more and more mass, the radiative core keeps on increasing. For the sun, we have seen that 70% from the inside the energy is transported radiatively, and 30%, the outer 30%, the energy transport is convective. Okay. When you reach 1.5 solar masses, the energy transport is entirely radiative. So, here the energy transport is entirely radiative, and then when you cross 2 solar masses, the core again now becomes convective. The core becomes convective. Once you cross 2 solar masses, the core becomes convective, and for masses more than this, the core is convective. So, here what happens is the core becomes convective, you have convection here, and the energy is transported radiatively outside for masses more than this. So, for masses more than this, the region where the nuclear fusion is going on, you also have convection taking place in the same place where the energy is generated. Okay. So, this gives you a picture of the solution, and whether energy is transported convectively or radiatively. Now, let me introduce the HR diagram. This is called the Hertzsprung Russell diagram, referred to as the HR diagram. And the HR diagram is one of the most useful methods for looking at stars. for understanding stars and looking at stars. This in this HR diagram, what is plotted in principle is as follows. So, in principle what is plotted is as follows. You plot log of the luminosity increasing this way versus the log minus log temperature. So, the temperature decreases in this direction, it increases this way. So, the luminosity, let me just put it here, it increases this way, the L increases in this direction, T decreases in this direction, because it is minus log T which is plotted. So, the more luminous an object, the higher up in this graph, in this diagram, it will appear, and the cooler an object is, the more to the right it will shift. Okay. So, let me again make this point clear, this side is cooler and this side is more luminous. That is how to interpret this diagram. In practice, you cannot observationally determine these two things. In practice, from the observational point of view, what is plotted, let me show that here. So, from the observational point of view, let me put it in a different diagram. So, from in practice, what you plot is, you plot the absolute magnitude in some band, let us say in the V band. And it is decreasing in this direction. So, it is increasing this way, right. The more the luminosity, the more negative the absolute magnitude will become. It is minus 2.5 log flux. Okay. So, it is decreasing in this direction, the magnitude is decreasing or the luminosity is increasing, right. So, the sense over here remains intact. Okay. So, the luminosity is observationally quantified through the absolute magnitude, the logarithm of the luminosity, and the temperature, I have told you, is observationally quantified through the color. So, you could use the B minus V color, for example. Okay. Or you could use the U minus B color, and these are the two things that are plotted along the two different axes. Say, let us say B minus V. So, this is a color magnitude diagram. It is a magnitude color magnitude diagram. So, bear in mind the color, let us look at the color. If the larger the value of the color, it means, if this value is larger, it means that the blue is fainter than the visual band. Visual band is at a lower frequency, larger wavelength. So, a larger wavelength having more radiation tells us that it is cooler. So, the more I go in this direction, the larger the value of the color, the cooler the star is. Okay. The more I go in this direction, the more luminous the star is. Now, a point which I should make, that early on when this diagram was introduced in the beginning of the end of the 19th century or beginning of the 20th century. When this diagram was introduced, this people had no method of determining distances to stars except for parallax. Even now there are very few direct methods, but the parallaxes were measured only for very nearby stars. So, there was no way you could determine the absolute magnitudes. What you had to do was, so you don't know what this number is for a star, you don't know the luminosity, but what you could do was you could look at stars which appear in a cluster. So, it could be a globular cluster or it could be an open cluster, but a cluster, and so the distance to the cluster is approximately the same from us. So, if you look at a collection of stars to which the distance is approximately the same, then the distance introduces a factor which is the same for all these stars. Okay. So, up to a multiplicative constant we know the luminosity. The multiplicative constant, the distance, affects all the stars equally. Or if you think of it in terms of the absolute magnitude, what you could measure was the apparent magnitude, but the apparent magnitude differs from the absolute magnitude by 5 log the distance, right, and the distance was the same for all the stars. We are looking at them in a cluster or in some kind of a cluster, in some kind of a group which is physically associated with one another. Okay, so, this is what people looked at, and what people found was that the stars, the bulk of the stars, lie along a band which runs diagonally across this diagram. So, the bulk of the stars, it was found, lie in a band which runs diagonally, roughly like this, across the diagram. Okay. And if you had a different distance, all that would do is it would shift this entire thing, right, because the distance would shift, that is all. So, the curve would go up and down for different clusters, different groups of stars, but it is found that for all of them the bulk of the stars lie on a band like this. This is called the main sequence. Okay. Now, later on, so this explain, so what it tells us is that there is a tight correlation. It tells us that there is a tight correlation between the temperature and luminosity. Of a star. And understanding this was a very big issue. What gives rise to this tight correlation between the temperature and the luminosity of a star, right. So, the bulk of the stars turned out to lie on a band like this. There were stars elsewhere also, okay, but this was a very dominant feature, and this was called the main sequence. It was later realized that these are the stars which are burning hydrogen. These are the hydrogen burning stars which lie on the main sequence. So, all the hydrogen burning stars in the HR diagram, they lie on a band like this called the main sequence. Okay. And it was later realized also that this we have discussed the equations, the fundamental equations governing this, that has been discussed, but it is not clear why they should lie on a straight line like this. We shall see later that there are simple scaling laws which give us some idea why the hydrogen burning stars should lie on a region like that. Okay, this is something that we shall discuss later. But things have changed since then, and there was a satellite called Hipparchus. This satellite was launched with the explicit aim of measuring parallaxes. Okay. To nearby stars, parallax distances to nearby stars, and it can, this satellite has measured parallaxes to an accuracy of 1 milliarc second. Okay, and it has measured parallax distances to around 100,000 stars in the solar neighborhood. So let me show you an HR diagram made with the Hipparchus data. It has around 17,000 stars within 300 light years. And focus on this particular diagram. Let me just draw your attention to this diagram, this particular HR diagram. So this is the HR diagram which has actually been measured by the of the stars. So this shows you all the stars that have been, whose parallax distances have been measured using Hipparchus. It has got 17,000 stars. Okay, not all of the stars, 17,000 stars within 300 light years. The luminosities are what have been measured. So this is the absolute magnitude, what has been measured using the Hipparchus data. The Hipparchus satellite measured the distances, okay, which goes into determining the absolute magnitude. The apparent, this is the difference of the apparent magnitudes in the B band and the V band, and this has been measured from ground based observations. Okay, Hipparchus basically gives the distances. So notice that the bulk of the stars lie on a band that runs from left to right across the HR diagram, and this is the main sequence. This, so all these are all stars which burn hydrogen. And these are the low temperature cool stars, relatively cool stars. As you move to the left, you go to hotter and hotter stars, bluer, right? You go bluer. You basically, as you move left, the color gets less, so you are going towards bluer stars which are hotter, and you find that the hotter stars are also more luminous, and the hottest stars that you have are the most luminous ones. So these are all the stars in the solar neighborhood within 300. These are all stars within the solar neighborhood within 300 light years. There, and this shows you the stars on the main sequence. Okay. Now these are not the only stars that you have. There are other stars also. Okay. Okay, before we move on, let me show you another HR diagram. This shows you another HR diagram. Here the HR diagram is of a globular cluster. A globular cluster is a collection of stars, is a distinct collection of stars, and so now here the distances to the individual stars are not known, but it does not matter because they are all at roughly the same distance. So I can interpret the apparent magnitude itself as an indicator of the luminosity. The distance has the same effect on all these stars. Now here again notice that you have the main sequence over here. This is the main sequence, but it extends to a much smaller distance along the HR diagram. And notice that there are deviations by, if we just compare these two. So right over here the main sequence kind of stops and you find stars which are off the main sequence. So this turning off from the main sequence is a very important effect, and we shall discuss this when we discuss the determination of this age, cosmological ages, the age of the universe. This is something that is very important for that. Okay, we shall come back to this point later when we discuss the evolution of stars. Okay. Now let us go back to our discussion of stars. So I have told you how stars can be classified using the represented and classified using the HR diagram. Okay. Now given for any star, given the luminosity and the radius, you can define the effective temperature right. So for given a star, if you know its luminosity and if you know its radius, you can define what is called the effective temperature, and we have already discussed this for the sun. For the sun, the effective temperature comes out to be 5800 Kelvin. Okay. Now if you compare this with the actual temperature of the sun at the photosphere, so for the sun this is the effective temperature. We have done this exercise. Now for the sun, if you solve the model, the stellar model which we have discussed, and if you determine the actual temperature at the photosphere, this comes out to be 6500 Kelvin. Photosphere, remember, is the region where the optical depth becomes 1. That is where the radiation originates from. That is the part of the sun that you actually see. The temperature there is higher than the effective temperature. This happens because some of the radiation, it passes through cooler material, it gets absorbed in the process. Okay, so typically the effective temperature is lower than the temperature at the surface that you are looking at for stars. Okay, but it gives you some idea of the temperature of the surface. So one could define this effective temperature for other stars also. And this is a very useful thing. Suppose I find a star, let me discuss this in a different sheet. Suppose I find a star, I find two stars at the same temperature. But two stars at the same temperature. One of them, L1, has a luminosity which is much less than the luminosity of the second star. then you would conclude that the radius of the second star is much smaller than the radius of the first of the first star is much smaller than the radius of the second star. Okay. So if I have stars and I plot them on the main sequence along the x axis I have the temperature, along the y axis I have the luminosity. So just try to visualize. So this is a star on the main sequence, let us say, and I have another star which has the same temperature as the main sequence star, let us say a very hot star, okay, same, and it is quite hot. So let me ask you, a hot star, in which part of the diagram would it appear? It would appear to the left. So a hot star would appear somewhere over here to the left. Now there is one star which lies on the main sequence, so there is a main sequence star over here, and there is another star which is much fainter. So what would you conclude? You would conclude that the second star, which is much fainter, has a much smaller radius. Okay, so it does turn out that you do get some stars like this over here in this part of the HR diagram of the main sequence. So these stars are called white dwarfs. So now you start to appreciate the utility of this HR diagram. You take any star and put it on the HR diagram. If you know its distance, or if you know it's in a group, then you compare it with the other stars. You do it just by placing it on the HR diagram. Okay, and if it lies somewhere much below the main sequence, but it is hot, then it's a white dwarf. It's an extremely hot star, but of extremely compact size. Such stars are not hydrogen burning stars, they are what are called white dwarfs. They are different kinds of stars, not like the ones that we have been discussing. They do not burn hydrogen at the center to start with, right? All the stars that burn hydrogen are over here. Similarly, let us look at the stars over here. These stars, are they hot or are they cold? They are quite cold, but they have extremely high luminosities. These stars, so you have a kind of star which is cold, right? So these are cool. So you have stars which are at relatively low temperature, but high luminosity. These stars are what are called giants and supergiants. Okay, giants and supergiants. So these are stars which are extremely not very hot stars, but they are extremely luminous. So their radius, the temperature is low, but the radius is large, basically R is large. These again are not main sequence stars. Okay, so these giant stars, they have a large radius, and as a consequence of that, their surface acceleration or surface gravity, which is g into the mass of the star divided by r square, this is relatively low. So these are not extremely massive stars, they are stars of typical mass which have typical like the sun or maybe somewhere around there, which have the radius has increased. So the surface acceleration has fallen, and as a consequence of that, what happens is that the density the acceleration is low, and as a consequence of that, the density, two things happen. The density is small at the surface, right. This is obvious because the r has gone up, the mass is fixed, and also the surface pressure is low. So, at the surface the density and pressure are both small, and this manifests itself in two ways in the spectrum of the star. So, the first manifestation of the density is that the density, remember, is there in the Saha ionization equation of any species, right. So, it affects the ionization of the species, that is one effect. So, the density comes into the Saha ionization equation and it affects the ionization state. So, this affects the ionization state. If you go back to your Saha ionization equation, you will see that it depends, the ionization state depends on the density, and a change in the density affects the ionization states. The pressure difference, the smaller pressure manifests itself in the line width of the lines. So, if you look at the spectral lines from the surface, the line widths reflect the pressure, and the more the pressure, you have the broader lines due to pressure broadening. So, for these giants you will have narrower lines, okay. So, the line widths get narrower because pressure is low, and from the looking at the spectrum, it is possible to classify a star as a giant, etc. Okay. So, there is a classification scheme which I had already mentioned. Let me tell you that. So, classes of the class 5 are the main sequence, class 4, these are the subgiants, class 3 these are the giants, class 2 these are the bright giants, and 1 these are the supergiants. So, the main sequence are the ones which burn hydrogen. So, let us go back to our HR diagram and take a look. So, these are the stars that burn hydrogen. Here, if in the local neighborhood, you also find the giant branch over here. There is another branch over here called the horizontal branch, which is kind of overlapping with the giant branch here, okay, which is more clearly visible over here. So, if you look at the globular cluster, this is a particular globular cluster M3. Okay, so the globular cluster is called M3 Messier on the Messier catalog. This is the main sequence. Here you have the giant branch. These are all giant stars of the main sequence, and here you have these stars which lie on what is called the horizontal branch. They are the horizontal branch stars. Now, if you take a look at this, you will see that there is a very interesting thing, that the brighter part of the main sequence is missing. The brighter part of the main sequence is missing, whereas you have this very extended giants. Okay, so this indicates that there is some relation, seems to indicate that there is some relation between these, and if you look at different globular clusters, you will then see that this turnoff occurs at different places. Okay, so the main sequence is where the stars first lead a large part of their life. When they are formed, when stars are first formed, they are formed in the main sequence. They lead a large part of their life burning hydrogen. Once they finish burning their hydrogen, then they depart from the main sequence, and then they become these other kinds of stars, the giants, supergiants. They go into the horizontal branch, some of them become white dwarfs over here, etc. And that is a very interesting topic, the life story of the evolution of stars, and that is something that we shall take up in the coming class. In today's lecture, what we learnt is that you have solutions for stable solutions of the equations that govern a star for only a finite mass range. Below that mass range, the stars do not, the pressure at the core, the temperature and density at the core are not adequate for fusion. Above the mass range, the Eddington luminosity is exceeded, the luminosity exceeds the Eddington luminosity, and the star blows away parts of the star itself. The luminosity is so high. So there is a finite mass range. Over that mass range, the range of radius is not very large, but the luminosities vary enormously. So if I go from here to here, the luminosities have changed by 10 to the power 8, something like that. Okay. The radius has not changed very much. The temperature also has not changed by an enormous amount. The colors do not change all that very much. Okay. They do change, the temperature does change, maybe of order 10 or somewhere of that order, but not like the luminosity. The luminosity is the thing that really increases drastically. Okay. And that is quite clear, it should be so, because the luminosity scales as T to the power 4, right. So a temperature increase by some amount will be a much more increase in the luminosity. So a combined increase in the radius and temperature will give rise to a large increase in the luminosity. Okay. And then I discussed how from the observational point of view, how stars are classified. You have a spectral classification, and you can get a real understanding of the stars if you place them on the HR diagram. So let me stop here. We shall resume on this tomorrow in the next class.